Previously, the two main approaches to memory management were manual management in C++ and Java's garbage collector. Now, newer solutions like Rust and Zig are available. This video introduces an alternative approach that follows the principles of C++, SRAI, and Rust's lifetime management, but implements them differently. Its advantages are readability and ease of use. In some cases, it is as simple to implement as a garbage collector. This approach uses only 3 keywords: run, up, and defer. Run is the most commonly used, while the other 2 are less common. The keyword names themselves do not have any special meaning. They were chosen for their simplicity, familiarity, pleasant sound, and ease of pronunciation. You can replace them with other names. The run keyword is used to mark class methods. When a method marked as run is executed, it will garbage collect the class and all its objects and member variables. It is somewhat similar to a C++ destructor, but unlike a destructor, the programmer only needs to mark the method with the run keyword and does not need to write the code inside the destructor. The keyword up can be used to mark class methods and functions. Any function not marked with up will have its newly allocated memory reclaimed when the function ends. After marking a function with the up keyword, newly allocated memory will not be reclaimed when the function ends, but will instead be reclaimed when the calling function ends. This keyword is used to optimize memory reclamation timing and is generally not needed. Note that, as shown in the middle, although variable a is not reclaimed in F2, it cannot be accessed. The up keyword only adjusts the reclamation timing and does not change the access scope. The keyword defer is used to reclaim external resources, such as database connections and file handles. These resources are requested by the program from remote programs. The program can only reclaim its own memory. The reclamation of remote resources is controlled by other programs, requiring a reclamation message to be sent to the remote program. The defer keyword handles this task. Let's first discuss the principles. Programs can be divided into 2 categories: procedural programs and server programs. Procedural programs execute continuously and terminate when they complete. You can think of a function as a procedure, although functions and procedures are not exactly the same. However, this comparison is sufficient for now. A key characteristic of procedural programs is that all memory allocated during execution can be reclaimed. Procedural programs interact with the outside world only through input parameters and output values. The other type of program is a server program. Server programs can remain in memory without executing any code, but they are not reclaimed automatically. For example, a web server is a server program. A defining feature of server programs is that their reclamation is triggered externally, not determined by the program itself. In contrast, the reclamation of procedural programs depends on the program itself. Procedural programs have a predictable end time, even if the exact time is unknown. Server programs, however, have no predictable end time. They might be reclaimed in 10 seconds or remain unreclaimed for 1,000,000 years. Both classifications can coexist within the same program. For example, the main body of a web server is a server program. When an external request arrives, the web server initiates a request handler to process it. This request handler is a procedure. Once the request handler has finished processing the request, it can be garbage collected, while the web server continues to wait in memory for the next request. Functions are not equivalent to procedures because, at a fundamental level, all programs are procedures. Server programs are also fundamentally procedures. Whether a procedure can be considered a server program depends on operations such as suspend, wait, concurrency, and callback. These operations are the nodes that mark the transition between procedures and server programs. We will not discuss this further here. Just remember that these nodes can affect memory reclamation. In this model, functions and objects define scopes. The scope of a variable is determined at the time of its declaration, following the principle of uniqueness and immutability, that is, the principle of zone-hosted uniqueness and unchangeability. Memory is reclaimed when the scope ends. Compared to Rust, which refers to scope as lifetime and ownership, Rust's scope is the same as its declaration scope. The difference is that Rust can use the borrow syntax to change the endpoint of the scope. Each time a variable is marked as borrowed, its endpoint is set to the end of the new function. In this model, however, this is not allowed. Once a variable scope is declared, it cannot be changed. Rust's keywords mark variables, while this model's keywords mark scopes. The compiler automatically analyzes variables based on their scope and associates the garbage collection point with the end of the scope. Since variables are automatically garbage collected when the function in which they are declared ends, and variable scope cannot be changed as in Rust, there are 3 ways to preserve variables created inside a function for use outside that function. First, declare them inside the function and enclose them outside. Second, declare them outside the function and use them inside. Third, store them in an outer class scope, which will be discussed separately later. Because of these limitations, this syntax forces programmers to develop programs according to a specific design pattern. In practice, it is not strictly mandatory. You can choose not to follow this pattern. However, if you do not, memory reclamation is likely to cause problems, so it is considered semi-mandatory. Consider this example. Suppose function f1 contains a variable a, and function f2 needs to use this variable. In Rust, you could simply borrow variable a. However, in this syntax, because scope cannot be changed, the scope of variable a at the time of its declaration must cover both functions f1 and f2. There are 3 ways to achieve this. One is to extend function f2, making f1 a subfunction of f2. Another is to extend function f1, and the third is to write a separate function f3, making both f1 and f2 subfunctions of f3. Some may find this syntax overly complex, while claiming that Rust's syntax is simpler and more flexible. However, the opposite is true. The code written using the syntax described in this video is genuinely simple, whereas Rust code is actually unreadable. For example, suppose a variable a needs to be borrowed 4 or 5 times. With this syntax, although it is a bit more cumbersome to write and requires a new function, the code is much clearer and more concise. Rust requires multiple borrowings. If a program has 4 or 5 such variables, each borrowed 4 or 5 times, the Rust code becomes almost incomprehensible. In fact, Rust can also directly assign an independent lifetime to store the variable a, allowing other functions to access this independent lifetime, just like this syntax. If you write code like the example on the left in Rust and find it messy and want to refactor it for clarity, you will eventually reorganize it like the example on the right. So why not enforce this approach from the beginning? Everyone knows that programs should be written simply, but the question is, what makes a program simple? In reality, a program with simple code is not necessarily simple. The essence of a program is the flow of data and functionality. Code in which the flow of data and functionality is immediately apparent is easy to understand. Code in which the flow is not immediately obvious is difficult to understand. Using this syntax, the data flow of the variable a is actually unidirectional, moving from its function to other functions, similar to the unidirectional data flow in the React framework. In the MVC pattern, data and functionality also generally flow in one direction, although this unidirectionality is not very typical because MVC usually has only 1 or 2 levels of abstraction. To use a real-world analogy, this unidirectional data flow is like organizing cables in a server room. Leaving the cables tangled does not affect functionality, but adding new machines becomes very difficult. In code, this means it becomes very difficult to add new features and troubleshoot errors. With Rust's borrowing syntax, the data flow is not easy to understand at a glance. The explanation above may seem complex, but in practice, writing the program is quite simple. This is because the programmer does not need to worry about garbage collection within function scopes. Resident data can only exist within the class scope, so as long as the programmer defines the class scope correctly, memory reclamation is essentially handled. Next, we will look at a more concrete example to demonstrate how to write the program as a whole. Suppose we are writing an FPS shooting game. The module architecture of this game is shown on the left. This game has 2 modes, 1v1 and 5v5. There is a module called Player that handles the logic for controlling the player's character. The programmer can write the code directly according to the logical architecture, as shown in the right diagram. A function is marked with the run keyword. This function acts as a destructor, except the programmer does not need to write the code, only mark it with the run keyword. These modules, or server programs, have a key characteristic. Memory reclamation is triggered externally. In this example, a game ends when the player presses the fire button, defeats all enemies, triggers victory, ends the game, and the game's memory is reclaimed. This includes an implicit convention. When a module is destructed, the memory of all its submodules is forcibly reclaimed. Submodules cannot be retained when a parent module is destructed. This follows the ZHU principle of zone-hosted unique and unchangeable. Additionally, this syntax semi-forces programmers to write programs using the architecture-oriented programming paradigm. This paradigm is explained in another video of mine. Here, we will only use it. In short, writing code in a logical architecture makes programs easier to write and read. The programmer writes the program according to the logical architecture, associates the destructor with a user-triggered action, and memory reclamation is essentially complete. It is important to pay attention to concurrent functions. Otherwise, there is nothing to worry about. This video does not cover concurrency-related design. Concurrency models are too complex to explain briefly and require a separate video. This design does not enforce unique readability like Rust's borrowing syntax. Instead, it allows programmers to choose their own concurrency strategies. Concurrency-related aspects require additional consideration. In some parts of the code, this approach is almost the same as in garbage-collected languages. For example, in web server projects where the MVC framework is pre-built, programmers only need to write request handler functions and do not need to write code related to garbage collection. The following discusses the drawbacks of this approach. This approach forces the use of a specific design pattern. For example, in a game scenario, both game modes have a player module. Creating a new player module every time a new game starts wastes performance. To optimize, the player module should be created only once and reused in subsequent games. Under this paradigm, it must be written as shown in the left diagram, while in C++ it can be written as shown in the right diagram. Clearly, the architecture of this syntax is clearer. The right-hand architecture is difficult to understand in terms of garbage collection. If there are 4 or 5 such submodules that remain in memory after the parent module is garbage collected, the garbage collection process becomes very difficult to comprehend. However, in real-world projects, programmers might prefer to write code as shown on the right because it requires fewer changes to the original code, carries a lower risk of introducing bugs, and prioritizes ease of modification and functionality. They may not care if the code becomes difficult to maintain in the future, as it is not their responsibility. While this is not a good habit, it reflects a genuine real-world need. Another drawback is reduced compilation speed. This syntax is similar to humans marking scopes, while the compiler automatically analyzes them, saving human effort but increasing the compiler's workload. However, I believe the performance overhead is manageable because machines will become increasingly powerful in the future, making this less of a problem. Machines will become cheaper, while human labor will become more expensive. In distributed system design, there is the CAP theorem. Consistency, availability, and partition tolerance cannot all be achieved simultaneously. The essence of the CAP theorem is actually a limitation of the physical world. Physics has an impossible trinity. Energy, mass, and information cannot all be obtained at the same time. Put more simply, it is about the finite nature of computer performance. If computer hardware were infinitely fast and energy efficient, the CAP theorem would not exist because you could synchronize data 1,000,000 times per second. If a design fails to meet a certain impossible trinity requirement, it means the design has not been pushed to its limits. This syntax prioritizes saving manpower over architectural conventions and compilation performance.